Thank you very much for that very nice introduction. Good evening, ladies and gentlemen. Before I start, let me thank the South African Institute of Physics for inviting me to come here and share some of the work we're doing at the Jet Propulsion Laboratory with you. It's a great privilege to be here, especially if I see so many young faces in the audience, and I hope that I will be able to give you some inspiration tonight, some of the things we're doing. You know, for thousands of years, people have looked up at the sky and wondered whether we are alone in the universe. I certainly did when I was a young child growing up in the northern part of Namibia. Here you see a beautiful video of us traveling through one of the star clusters in our universe. And it's in places like this that stars are born, particularly in those features that look like pillars sticking out of the dust cloud. These are interstellar dust clouds. And when the dust is compressed in these areas, enough so that the dust becomes dense enough, they start accreting dust from around them and eventually form stars like the ones you see in the picture there. Now, theory suggests that once a star is born, planets are formed out of the so-called debris disk of leftover material that was present when the star formed. Over time, little chunks of this material coalesce together. They start attracting material around them, and pretty soon you have an object large enough to become a planet. That's basically how we believe our solar system started. Originally, it was a disk like this, and over time, the planets basically ate up all the material around them, accreted them into larger and larger planets. Now, when you look at the sun like ours, and the system is now stable, then there's a well-defined distance away from that sun where the temperature drops enough. Our sun is around 6,000 degrees. So if you go away from the sun almost to the orbit of Venus, the temperature drops enough so that liquid water can actually exist. If you get closer to the sun, it'll just boil off and evaporate. If you keep on going further out, you'll get to the point where the temperature is such that water would eventually freeze. That happens just on the outside of the orbit of present-day Mars. So that little turquoise band that you see in our solar system there that contains Venus, the Earth, and Mars is known as the habitable zone. And it's in this zone that scholars tell us we should look for the signs of life. Now, if you actually look at the three ingredients that are required for life to exist, you will find that these things are liquid water, at least life the way we know it, requires liquid water. You need the conditions in which complex molecules can form. And then thirdly, you need some kind of a source of energy that can sustain metabolism. So the conventional wisdom is that we have to look in these habitable zones. So for every star, once we know the temperature, we can calculate how far away from that star we have to be in this so-called Goldilocks zone where liquid water can exist. In our own solar system, as I said, it stretches from the orbit of Venus to the orbit of Mars. Here's a picture of Venus on the left. It's a very dense atmosphere. So we cannot see the surface of this planet unless we use a synthetic aperture radar, which is my specialty. On the right-hand side, you see an image of the surface of Venus taken with such a radar system that we sent there in late 1980s, early 1990s. And it shows an impact crater on the surface of Venus with the ejecta blown out when that object hit the surface of Venus. The surface of Venus today is hot enough to melt lead. So even though it is within the Goldilocks zone, the surface temperature is far higher than we would be able to sustain liquid water on. And that's because it has a very dense atmosphere and a runaway greenhouse effect going on. So let's look at the other edge of our solar system. We know in the middle there's the Earth. We know there's life. We can argue forever whether that life is intelligent, but there's life on this Earth. So let's look at the next planet over, our neighbor to the outside of the solar system, Mars, which you see a beautiful image of here. Comparing Mars to the Earth, you see here the relative sizes. Mars has a radius about half of that of the Earth. The gravity on Mars is about 1/3 that of the Earth. So if you go there, you will weigh about 1/3 that you do on the Earth. Great, easy way to lose weight, but don't come back. You'll gain it all again. The atmosphere of Mars is much, much thinner than that of the Earth. The pressure on the surface is less than 1%, and 95% of the atmosphere is carbon dioxide. Only less than 1% is oxygen. So you will not be able to breathe and live on the surface of Mars today, unless you have some special breathing equipment. But these two planets share a lot of common features. As you can see in this particular image, the North Poles in both cases have ice caps on them. Both of them have large canyons on them. On your right-hand side is the Grand Canyon in the United States, the largest canyon on our planet. It's about 400 kilometers long. It's about 20 kilometers wide and about 1.6 kilometers deep, a mile for the older people in the room. On your left is a series of canyons, Valles Marineris on Mars, 4,000 kilometers long, 10 times as long as the Grand Canyon. It's 200 kilometers wide, and it's about 7 kilometers deep, much, much larger than the Grand Canyon on Earth. Both of them have great volcanoes. The highest mountain on Earth is Mount Everest, about 8,800 meters. Olympus Mons on the right-hand side of the slide is a volcano on Mars that is 21,000 meters high. The cliffs at the edge of that volcano that you see there are higher than Mount Everest on Earth. So a very large mountain indeed. It covers about, if you look at the size of Namibia, it covers about 1/3 the size of Namibia. It's this volcano. And both of them have interesting geology. In fact, I often ask my students in my class if they can pick out which one of these two pictures were taken on the Earth. I'll let you in on a little secret. If you look very carefully in the top left corner of the right-hand side picture, you'll see a van parked there. That's how I can tell which one is which. Mars is on the left. The Atacama Desert in Chile is on the right, the driest desert on Earth. Very, very similar geology. But believe it or not, until 2004, we had no actual proof that there was ever water on Mars. So in 2004, NASA sent two of these little rovers that you see here to Mars. They arrived there in January of 2004. They were called Spirit and Opportunity. And their job was to go there and basically be a roving geologist to find evidence if there was ever water on Mars. Images from our satellites that orbit Mars showed the presence of a mineral called hematite on the surface of Mars. Hematite is an iron mineral that typically forms in water on Earth. So their job was to go there. We picked the landing sites to be in those areas where we observed the hematite from orbit. And their job was to go look for that. This is what the Earth looks like from the surface of Mars. Not a very impressive dot in the sky, as you can see. Here you see a series of pictures, animated, showing little dust devil winds blowing past one of those rovers. It was, in this case, it was Spirit that was parked on the plains. These rovers originally were thought that they would last about 90 days on Mars. The limiting factor was that we thought that dust on Mars would accumulate on the solar panels and basically in the end block out the sun. Well, it turns out these little winds come by regularly, almost every day on Mars. And sure enough, the dust indeed collects on the solar panels, but these winds would come by and blow them off again. And then we can drive again. So as a result, one of the rovers is still operating, even though it landed in January of 2004. Now, when I tell my students this in my class, they often point out to me that that's a massive failure of design if you promise 90 days and you'll last for 11 years. This is a beautiful picture from one of our satellites orbiting Mars of a crater called Victoria Crater. And if we zoom in a little bit, you can see one of those little rovers, in this case Opportunity, right at the edge of that crater. And if you look very carefully, you can see it's labeled there, the rover tracks. You can actually see as it was driving around trying to find a place to drive into the crater, which we eventually did and studied the rock formations in the wall of the crater. On Mars, we are very lucky that there are these large craters that basically excavated the subsurface for us, so all we have to do is drive into them and we can actually see what the subsurface looks like. The rovers very quickly found, in fact, these little gray spheres that you see here. Looks a little bit like blueberries in a muffin contained in that rock there. The circular feature is caused by a little brush that we have on the arm of the rover that can clear off the dust from a rock so we can see what the actual rock looks like. But anyway, these little spheres are actually the hematite. So the rovers actually did go there, found the mineral that formed in water. So this, ladies and gentlemen, is your proof that there was indeed water on Mars at one point in time. They also looked for other ways to see if there was water before. And this is a beautiful image of Burns Cliff inside a crater called Endurance on Mars. Basically, what you can see here are layered rocks, which are sedimentary rocks laid down by water. An analysis of these rocks showed that the water flooded this area episodically and then dried out again. But the chemical analysis of the rock showed that the shallow sea that existed in this area was probably quite acidic, so probably not a good place to find life. In any case, these rovers proved once and for all that water was indeed present on Mars at one point in time. So following that discovery, NASA decided to send a more capable rover to Mars. And this time we would want to answer the question, were the conditions on Mars ever such that it could have sustained life? Here you see that rover called Curiosity that was sent to Mars. It's much, much larger than previous ones. It weighs 1 ton and is about the size of a Mini Cooper car that we launched to Mars. Here you see the spacecraft being prepared before we launched it to Mars in our environmental test chamber. The rover is, in this case, tucked up inside that cone that you see there. The black surface that the person is touching is the heat shield that protected this entire spacecraft as it was going through the atmosphere in Mars. So I'm going to show you a quick video of how this landing happened. Basically, because this rover was so heavy and so big, we could not use airbags like we did in the past to protect the rover when it landed on the surface and basically bounced around for a while and then drove off. In this case, the rover was far too big for that. And we had to come up with a new way to do this called the sky crane. You will see in the video we enter the atmosphere of Mars. At that point, we're traveling at about 21,000 kilometers per hour with a total spacecraft that weighs about 3 tons. Now, keep in mind that this entire project costed $2.4 billion American dollars. So you do not want this thing to splat on the surface. So we had to carefully dissipate the energy from that system and land gently on the surface. It takes only 7 minutes to go through the atmosphere and land on the surface on Mars. The signal takes 14 minutes to get a radio signal, takes 14 minutes to get from Mars to us. So at JPL, all we could do was watch what happened 14 minutes earlier. There was no way we could interfere or intervene at all. Everything was completely autonomously done by computers. So in the video, you will see us entering the atmosphere. Even though the atmosphere is much thinner than that of the Earth, this capsule still heats up to about 2,500 degrees. That's where that black surface comes in to protect us at that point. The atmosphere slows us down with drag till about 1,600, 1,500 kilometers an hour. And at that point, the atmosphere runs out of gas, and we cannot slow down with the atmosphere any further. So we open a special supersonic parachute. That parachute is about 20 meters in diameter. It slows us down to about roughly 300 kilometers an hour, and at that point, it runs out of gas, and we cannot slow it down any further with that. 300 kilometers an hour is still far too fast to land. So at that point, you will see us drop this heat shield off, and then the rover will pop out of that shell And it has its own jetpack, special rockets that fire up, and those rockets then fly us down to the surface, where we hover above the surface and then lower the rover down with cables. Once we touch the surface, we cut the cables, and the so-called descent stage just flies away. So fasten your seatbelts. This is how the landing went. So at this point, we're starting to heat up, as I said, to about 2,500 degrees. You can see the drag for the atmosphere. We then open the parachute. Once we reach that 300 kilometers an hour, we pop the rover out, and the rockets light up, and we fly ourselves down to the surface, hover above it, and then lower the rover on the cables down to the surface. These people didn't even work on it, and look at how nervous they are. And then we finally fly away, and you can see even nerds can get excited about something like that. So here we are, safe on the surface of Mars. First pictures that came back. You can see the shadow of the mast and the arm of the rover in front of us here. The gray holes you see there and here, those are the blast holes from the rockets as we were coming down to land on the surface. And in the background is a mountain called Mount Sharp. This is a mountain made up of layered materials, layered rocks, and we hope to drive up it and study how the history on Mars changed over time. So starting at right out of the bat, so to speak, we found the evidence we were looking for. Here is a rock called a conglomerate. On Earth, geologists will tell you conglomerates form in water. Basically, larger rocks are cemented together by sand and so on. And so we were lucky enough basically to land in an ancient stream bed on Mars. We first started at the at the landing site. These two little black, that's where we landed. And if you look carefully, you can see the tracks of the rover as we were driving here toward this lighter colored area. The reason we wanted to go there first, which is, by the way, away from the mountain, is that our orbiting satellite showed us that this area contained clay minerals. Again, clay minerals form in water, and we wanted to go look at this area and see if we could analyze it to tell us what the conditions were like on Mars in the past. If you look carefully, you can see the rover here as the little bright dot. These images from orbit have about a resolution of about 30 centimeters, so we can quite easily see the rover. This is what that area looks like when we got there. Very much like the deserts of Namibia and other places in the world. In fact, when the rovers landed in 2004, I remember my wife said to me, "Oh my God, they landed in Namibia." So you can see why. I think I would be right at home in this place. A couple of other pictures of what it looks like, a couple close-ups. For those of you who've driven through the Namib Desert will recognize that this looks pretty much like the Namib Desert. Now, Curiosity has its own drill with which we can drill holes into the rocks to analyze what the interior of the rocks are made of. Here you see the first 2 holes ever drilled on another planet besides the Earth. And believe it or not, just this color picture that you see here is the first major discovery from Curiosity. The fact that the interior of the rock is gray is the discovery. Theories in the past suggested that this red color, basically the rust, the oxidizing layer on Mars, would extend at least 1 meter or so into the surface. And that would preclude any life from existing near the surface of Mars. Well, we drilled only 1 centimeter or so into the rock and it's gray. So there goes one theory. We've got to think about something else now. So we then picked up some of this gray material, and you can see a little scoop there on the left-hand side. That scoop can pick up the material, and then we put it inside the body of the rover. We have very sophisticated instruments called mass spectrometers with which we can look in detail what the composition of the rocks are. And basically the short answer is, we found that this area had sustained water for a long period of time, probably thousands of years. It was either at the end of a river system or a dry lake bed, which at the time was, of course, wet. Furthermore, the water was of such a quality that we, humans, would have been able to drink it. So clearly this area on Mars would have been able to sustain life. Very quickly answered the question for which we went there originally. Yeah. Leaving that site, we started driving towards the mountain to go study further what the conditions were over time in Mars. As I mentioned, the measurements in the bottom of the crater showed that it easily could have sustained life. So what happened? Why is it today looking like this? Here you see some nice tracks of the rover as we crossed a little dune in a place called Dingo Gap. We have kind of interesting names for these places. By the way, the Namibians always send me emails offering to drive the rover through the sand for us and stuff like that. Closer to the mountain, this is what it looks like. Still plenty of evidence of past water, including these layered rocks that you can see here. Now, just recently, Mars was exactly in the opposite side of the sun from us. So we could not communicate with the rover. You see it basically parked here, right there, it's a little rover. We parked it for a week or two while the Mars was just behind the sun from us, so we couldn't communicate with it. Basically told it, just wait there until you hear from us again. And it just came out from the other side of the sun again. So within a couple of days, we will start driving again and continuing our search for the changes in the history on Mars. On the way to the mountain, however, we encountered some interesting terrain that the rocks were basically so sharp that they were puncturing this metallic wheels of the rover. You can see a big hole in the top of our wheel there. And here's another nice big chunk out of the wheel. Now, when the nearest tire shop is a couple of 100 million kilometers away, you got to take care of the tires of your truck. Fortunately, we have figured out why that happened. As I said, it was an area with very hard rocks. Most of the time, when we drive over rocks, we just press them into the surface on Mars. But when the surface is hard enough, the rocks basically will just puncture the wheels. So we have now learned how to identify that kind of terrain and just don't drive over it. So we drive around it. So we should be good for quite a while to go. Here's one of the other interesting discoveries of Curiosity. We measured the amount of methane in the atmosphere where we are. And for a long time, we see nothing really happens. But then there was a sudden spike where the levels of methane went about 10 times as high as it was before. And then after a while, it came back to the original values again. This is the life of science. You find an interesting discovery and open 20 other questions. We don't know why this is happening. People have seen similar spikes in the methane in the atmosphere of Mars with telescopes before, but we do not know why this happens. That's an interesting question that we will continue to pursue. Another interesting discovery is an organic material called chlorobenzene on the surface of Mars. Here are 4 areas where we analyzed samples. The first one was just a scoop of material we picked up called Rock Nest, then John Klein's site, and then comes Cumberland, and suddenly we see a very high level of this chlorobenzene molecule. We know it is chlorobenzene because we can compare the measurements we make on Mars with laboratory samples here on Earth. That's the little inset that you see there. The red is on Mars and the black is on the Earth, and you can see the spectra match very well. And then at Confidence Hills, it's low again. A very interesting discovery. We did not know that these kinds of organics exist on Mars. Well, but the story is only half of the story is told on the surface. The other half is from orbit. Here you see a series of images taken by one of our orbiters that shows these streaks forming during the Martian summer. Basically starts in the springtime. This part of Mars during the summer gets above freezing. So what you're seeing is basically believed to be briny water seeps. There's ice close enough to the surface that when the summertime temperatures get high enough, the ice melts and the water slowly seeps down the side of the slope here. Now, we cannot drive up to these slopes with our rovers. It's far too steep. So we will have to figure other ways to get to these areas. And in fact, NASA just agreed to give us some money to test a little helicopter. Here you see a scale version of it being tested in our chamber at JPL. We've pumped the atmosphere out to be the same as that on Mars. And you can see this little thing lifts up. Doesn't look very sexy, but it works. It will carry a little camera on it and a radio with which we can then communicate back to the rover. The plan is to take this, if we can develop it in time, with the next mission to Mars in 2020. We will use it at this point in time to fly ahead of the rover and scout the terrain so we can drive more efficiently than we do now. But eventually we hope to put more capable scientific instruments on it and make them larger, of course, and then to fly potentially to places like those SAIPs. What makes this interesting is, remember, the light time, travel time from Mars is in minutes. So there's absolutely no way a human can actually fly this thing from the Earth. It will have to fly completely by itself, under its own computer control, take off, land, recognize where it is, where there are no GPS receivers. It'll have to recognize the terrain and come back to the rover every night to download the images. Well, those images from orbit showed that there may be water on the surface of Mars today. It doesn't stand in ponds and things like that, but it's very close to the surface. So if that's the case, maybe there may be some underground areas on Mars where it would be moist enough for life to exist. Here you see two entrances to caves on the surface of Mars that we spotted from our orbiting spacecraft. And if you zoom in a little bit, you can stretch it a little bit, you can see what the inside of the caves look like. So we would very much like to go to these places and look at them in more detail as well, crawl inside. Now, in order to do that, of course, we cannot drive in there with a rover, and you cannot fly in there with a helicopter. So we are working on little gecko rovers like this one at JPL. My wife likes it so much she just wants to bring it home. She thinks it's really cute. You can see it climbing here on a vertical wall, and in just a second it'll show you how it can actually climb along the ceiling, upside down along the ceiling there on the surface. Hopefully we will be able to go into caves like that on Mars and other places, other planets potentially. Excuse me. To study the subsurface in these areas. Well, let's move away from Mars a little bit further out to Jupiter. And Jupiter has one moon in particular that's of great interest to us. It's called Europa. You see it here in front of Jupiter. Jupiter, of course, is the largest planet in our solar system. You can fit 300 Earths inside of Jupiter. This moon, however, is about the size of our moon. And this is what it looks like close up. You see there's only one crater on this, visible on this surface of this moon, which means that geologically this is a very young surface. If you look even closer, you see that the surface is covered with large linear features like this, which we believe are cracks in the surface of that moon. Basically, this moon is an ice shell with an ocean underneath it, and you will see how we get to that conclusion in just a little bit. If we zoom in even further on one of those areas with the cracks, this is what it looks like. The bluish, whitish areas are pure water ice, and the reddish areas are water ice mixed with salts. The salts have been radiated by the strong radiation from Jupiter, and it turns them brown like this. Here's another interesting area with these little dots on them called lenticulae, which is just the Latin word for freckles. I don't know why we just don't call them freckles, but anyway. They're about 10 kilometers across, and they are areas where we believe that the ice has melted in the past, and water may have seeped all the way through the ice shell to the surface, bringing the salts to the surface, hence the brownish color in those circular features. And then in the extreme case of these is what we call the chaos region. So you can see one up here. It's basically this area there, and on this here. If you look carefully inside that area, you will see some blocks of ice. It looks like blocks of ice that has broken apart and then floated a little bit and then froze again. This is very much like what happens in our Arctic oceans with the sea ice. It eventually breaks into chunks and then it could freeze in between them again and freeze them in place like that. If you look at it, it looks like this whole area was sort of collapsing with the cracks on the side there. These chaos areas are where we believe that a large plume of hot water or from the ocean made it all the way to the surface and almost made a pond on the surface of this moon. There are two theories of what is happening on this moon. The first is that there is a relatively thin ice crust, maybe a kilometer or so thick, maybe even less, and that there is a large ocean about 60 to 100 kilometers deep and completely global on this moon. The interior of the ocean is heated from below by volcanism from the mantle of this moon. The whole interior is heated up by tidal flexing as this moon is orbiting Jupiter. These plumes of hot water then move to the surface and can eventually melt those chaos regions and so on like you see there. Also through the cracks you can see a possibility that some of that water vapor may actually escape into the air around this moon. The second theory is that the ice is much thicker, probably on the order of 30 kilometers or so, and that the ocean is then a little bit less deep, but even so the ice is melted or heated from the bottom, and plumes of hot ice slowly migrate to the top, somewhat like glaciers on the Earth, and then eventually make their way to the top. In either case, there is a large ocean on this moon covered by an ice crust. If you compare Europa to the Earth, as I said, it's about the size of our moon compared to the Earth there. The little water bubbles show you the relative amount of water on these two places. Basically, Europa could have twice as much water on it than the Earth has. So a prime place for us to look for a potential of life. It has heat, it has a salty ocean. We know that because it modifies the local magnetic field of Jupiter, so it has to be a conducting medium, and it has liquid water. So a perfect place for life to exist. We are currently studying a mission to go to this moon, launching somewhere in the early 2020s, and we will carry special instruments, including a high-powered radar with which we will be able to penetrate through the ice to see how thick the ice is. We can once and for all decide which one of those two theories is correct. We also will carry special spectrometer instruments which will tell us the chemical composition of the surface of the moon, so we can better understand this very interesting place in our solar system. So moving a little bit, I should not forget, there is a powerful congressman in the United States that would like us to land on the surface. We are currently working on little studies like that to see if we can put a small lander on the surface. This is, of course, an artist rendition of what the surface might look like. We don't believe that it's technically feasible for us to land something on this moon by 2020, but then again, we have a lot of smart people. They might figure out a way before we know it. Moving further out to Saturn, the second largest planet in our solar system. Here you see a picture of it taken by the Cassini spacecraft with its beautiful rings around it. Now, Saturn has more than 60 moons. And here is a very interesting one of them, Hyperion. This entire moon has half the density of water. So, believe it or not, this moon would be able to float on water. It looks like a sponge, as you can see here. It's a very interesting object that we do not quite understand yet. We believe those holes in the sponge are actually places where small meteorites hit it and basically just went right into it. Maybe even right through it. We don't know for sure. But we went there actually to study originally this moon of Saturn called Titan. Titan has a very thick methane atmosphere. And some theories suggest that the primordial Earth may have been similar to this, with a thick methane atmosphere like this. In fact, here you can see through the limb of the moon, the hazy atmosphere, the bluish methane layer that you can see there with Saturn in the background. The Cassini mission launched a probe called the Huygens probe with the European Space Agency to actually go into the atmosphere and land on the surface of this moon. Here you can see a picture that probe sent back before it actually died. And you can see a very hazy surface with rocks all over the place. Looks kind of interesting. Now, Cassini also carries a synthetic aperture radar with which we can see through those hazy atmosphere the surface of the planet, this little moon. And here you can see a large lake with a river system that drains into the lake, making Titan the only other body that we know of in our solar system that have actually rivers on it today that are active. The difference is these rivers do not carry water. They basically carry gasoline. So imagine if you could just drive your car up to the river and fill it up. You just don't smoke on a place like that, I suppose. But this moon, called Enceladus, is the one that intrigued us the most in the end. Here you see a beautiful picture taken of Enceladus by the Cassini spacecraft, which shows what looks like 4 plumes coming out of the south pole of this moon. A close-up shows, in fact, that those plumes go quite a ways into the air, like 100 kilometers actually into the air. So we asked our navigators to take that spacecraft and bring it as close as possible to that moon so we can see if we can find out what those plumes are made of. And they responded by flying the spacecraft 25 kilometers above the surface of the moon, right through those plumes. I guess you shouldn't challenge a navigator after all. A fantastic feat if you think that Saturn is more than 1 billion kilometers away from us. So a very, very small margin of error. This is what that moon looks like if we take a little bit closer look at it. Part of it appears to be an older surface. You see a lot of craters on it. But the southern hemisphere, with those blue stripes on it, don't have any craters on it. Again, that indicates it's a very young surface geologically. And if we zoom in a little bit on those areas, you see the cracks look very similar to what we see on Europa. And in fact, we have now determined that the plumes that we observe come out of those cracks. Thermal imaging shows us the cracks are warmer, in fact, than the surrounding ice, quite a bit warmer. And in fact, that is where, as I said, the water plumes come out of. What are they made of? Mostly water vapor. Salty water with actually simple and complex organics in it as well. So a second place in our solar system, not in the habitable zone, where we have liquid water, we have organics, and we have heat. Another place where we can look for life. Recently, people have shown that many other moons around both Jupiter and Saturn could also have global oceans on them. Of course, all covered by an ice crust today. So this suggests that we may have to rethink completely our theory of what habitable means. And it's not just the habitable zone of a star that we have to look at, but also places like giant gas planets like Jupiter and Saturn. And their moons could potentially also be places where life might exist. But what about, so here's what the current model is of what Enceladus looks like. It has at least an ocean in the southern hemisphere where the smoother surface is, and that the water from that ocean basically escapes through the cracks in the ice crust. So, but what about outside of our solar system? Are there places outside of our solar system that could potentially harbor life? In 1584, Giordano Bruno speculated that that in fact is the case. You can see here a quote from him: there are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. At that point, they still thought the sun was a planet. We see only the suns because they are the larger bodies and they are luminous. But we do not see the planets. They remain invisible to us because they are smaller and non-luminous. Basically, you have to block the sunlight out just like when you look to the sun, which, by the way, I don't recommend you do. With your naked eye, you should always put something between you and the sun. But when you block it out, you can see stuff near the sun. Well, that's exactly what Giordano Bruno said. He got burnt at the stake for his trouble. These days, we are a little bit more tolerant of crazy ideas than that. But let me tell you how difficult it is to make an image of a planet around another star. Here you see an image of the Earth at a resolution of roughly 160 kilometers. If we take the Earth and we move it to the nearest star to our sun, 4 light years only away from us, and you want to make a picture like this, you need a telescope that is 15,000 times the size of the Hubble Space Telescope, the largest telescope we've ever flown. To put that in context for you, the mirror of that telescope would almost fill False Bay. And if you put the telescope on the ground, it'll be over 200 kilometers long. So that'll be a little bit difficult for us to get something like that into space. So this is clearly not a very practical way for us to take pictures of planets around other stars. And remember, this is only the nearest star to us. If you want to look a little bit further out, then you'll have some difficulties. Fortunately, there are other ways we can find planets around other stars, and here's one example. It's called the transit method. When a planet comes between us and its parent star, it'll block a little bit of the light away out while it's in front of the star, as you can see there with the little graph. So if we could look at this star all the time, and we see periodically that the light of the star just goes a little bit dimmer and then comes back up again, we know that there's something that's orbiting that star, and it comes between us and the star every once in a while. The amount by which the light dims depends on how big the planet is. The bigger the planet, the more the light will dim. The smaller the planet, the less it'll dim. And of course, the time in between when this happens tells you how long it takes the planet to move around the star. To find an Earth this way, or around the star similar to the sun, means that the light only dims by 20 parts per billion. Very, very little. But we were able to build a camera, and you see the focal plane of here. It's a 100 megapixel camera that is a very, very stable camera that can find little changes like that, 20 parts per billion. We put it into a medium-sized telescope there. It's about 1.5 meters in diameter, the lens, and launched it in 2009. It's called Kepler. Some of you may have heard of Kepler. Kepler has found around 4,000 candidate planets so far, of which we were able to confirm more than 1,000 of them. So let me show you the history of finding planets within our solar system and outside. We start at 1755. You'll see soon Uranus appear there. And then Ceres appears for a little while, until about 1860 or so, and then it gets demoted to an asteroid, and so it disappears. We have back to 8 planets again. In 1930, Pluto will appear, but as you all know by now, Pluto was kicked out of the club too in 2006. So Pluto will hang around for a little while. And in 1995, you will see we will find the first planet outside of our solar system. And then we start finding more and more of them. But Kepler only launched in 2009, and the planets found with that technique called the transit method that I showed you are shown in green here. So starting in 2009, which we're about to reach, Kepler launches, and you start picking up the green ones. And you'll see in 2013, 2014, we announced a lot of planets. And basically, many of them are closer to their sun. If you look at this axis here, there's the Earth. It takes about 1 year for the Earth to go around their sun. These guys are much closer to their sun than our Earth. Here is the size. That's the Earth. Many of them are smaller than the Earth, actually. We found very interesting differences in the planetary systems. Here is an example of Kepler 186. I use this as an example because it has one planet that actually orbits within its habitable zone. You can see the relative size of Kepler 186f. Now, if you've ever wondered why we call them Kepler 186f, First of all, we don't have names for all the suns, so we just number them. Kepler, this is the 186th star that Kepler was looking at. And you start naming the planets B, C, D, E, and F. So you keep on going with the alphabet. A, of course, is the star itself. This is a so-called M-dwarf star, which is much cooler than the sun, which means that its habitable zone is much closer to the star than ours. In fact, you can see it's about the orbit of Mercury. That takes this planet, Kepler 186f, about 130 days to go around its orbit. Much closer, but nevertheless within its habitable zone. We found other planet systems which have a Jupiter-sized planet that goes around its sun every 4 days. Very, very different than our solar system. So what do we do in the future to try and image some of these planets? As I said, you have to block the light from the sun out. So we're working on a concept known as a star shade. You can see here, it's basically like a flower petal that you unfold when we get on orbit. We take this screen and we put the screen between us, our telescope, and the sun. And as we move it into place, you can start seeing the planets revolving around the sun. The diameter of that flower is roughly 40 meters, and it will fly a couple of thousand kilometers in front of the telescope. We're working on this. The technology should be ready in the mid-2020s to launch on orbit, and we are hopefully going to fly this with a telescope called AFTA that NASA is planning to launch, which has a mirror the size of the Hubble Space Telescope. So with this technique, we hope to be able to find many more planets. So as you can see, we have learned a lot in the last 10 years or so about how our solar system works, where we can look for potential signs of life in our solar system. We have realized that we need to change the definition of what we call habitable and include the icy moons. And of course, there's much more to be learned about the planets outside of our solar system. So for the younger folks in the audience, I hope I have inspired you to take on this quest, because I don't think we will find them in my lifetime, but I hope that in your lifetime at least, one of you might find the signs of life elsewhere in our universe. Thank you very much for your time.
What a wonderful talk. This talk is now open for questions. We have 2 microphones in between in the aisles, so if anyone wants to ask a question, please come forward, and Dr. Jaapie van Zyl will answer your questions.
I hope I can answer your question.
Okay, so on the right-hand side.
Yes, thank you very much. How many planets are estimated to be in the habitable zone in our galaxy? That's my first question. And the second question is there any possibility of using optical aperture synthesis? I'll just explain it for those who don't know. It's combining light from telescopes that are far apart, whether it's in space or on the Earth, in order to image some of these planets.
Yeah, thank you for that question. One of the things I forgot to mention is that, as I mentioned, Kepler found roughly 4,000 candidates for planets, of which we have now confirmed about 1,000 of them. The reason I say confirmed, we have to follow up with other observations to make sure that these are indeed planets and not just double stars and things like that. Now, remember, we can only see the planets that actually come between us and the star. And if you look at a star, it's a relatively small dot in the sky. So there's a very narrow range of angles for the orbits of that planet for us to be able to see them. If you take the statistics into account of Kepler, basically assuming that, from star to star, planets can orbit in any direction around them, then you will find that the statistics suggest that in our galaxy alone, the Milky Way galaxy alone, there should be about 50 billion planets. And a staggering 500 million of those should be in the habitable zone. So again, the Earth is not nearly as special as we had thought before. There could be many, many other places, only in our galaxy. And keep in mind, Depending on whose count you believe, there are a 10 with somewhere between 11 and 13 zeros galaxies out there. So multiply 50 billion by another 10 with 10 to 12 zeros on it, and boy, that's a lot of planets. The other question you had about the combining light from large telescopes that are far apart, that is, of course, a way in which we can get much more narrow, what we call angular resolution, basically better ways of pointing down where something is. We have made many studies of that. The technology, in fact, exists. We have proven that at JPL. You can take light from different sources, combine them together like that. In fact, we do that on the island of Hawaii today, where we have two 10-meter telescopes separated by 85 meters. And we combine the light from those telescopes, and basically what you get is the resolving power of an 85-meter telescope. So with that kind of a technique, we've been able to measure the actual diameter of stars. Now, eventually we want to put that in space, but that's, many years off. We need very large telescopes. Right now, we're struggling to get one into space. For that, depending on which concept you're looking at, it's 3 to 4 telescopes that we will launch like that. But it's coming. It's coming. We'll do it eventually.
Can you use the microphone, please? Maybe wait the microphone. There's a gentleman behind you.
If you could just explain the telescope array. How does that relate to the telescopes in space? Because South Africa has got, and Australia, this really large radio telescope project.
Correct.
How does that relate?
It is basically the same kind of an idea that we just talked about, combining light from different telescopes. In the case of the square kilometer array, which is what you're referring to, that will be here in South Africa and in Australia, we use radio signals, much longer wavelength, but it's the same principle. You take a lot of these dishes and you combine the light from those dishes, and you can create the equivalent of a very, very large telescope that way.
Thank you. What do you do to protect your electronics against radiation, and what's your experience with that in outer space?
That, of course, is one of the big issues for flying in space. There's much more radiation out there than we have on the Earth. Thank goodness our magnetic field protects us from that. Basically, what we do is we very carefully screen electronics, and then we design the circuits such that if a particle hits one of the parts of this circuit and it latches up, that the circuit protects itself so it doesn't burn out. It took, of course, a lot of experience to get to that point, but these days we are very good at protecting our electronics that way. You can shield to some extent the electronics from these particles, but that adds weight. And weight is a very expensive commodity in space. So we try to keep our spacecraft as light as possible, which means we cannot shield it that much. So we basically do it with careful design of the circuits.
When we look at the ages of the, shall we say, evolution of the development of man, from very primitive chemicals, methane, carbon, and that, to the stage we are now, then we are only a minuscule second in the entire time span for which these planets exist. Now, could you speculate, or can anyone speculate on the possible advanced life forms on some of these planets, which are much older than the Earth?
That's a very excellent question. If you think about the Earth, people have often said, why don't you just listen and see if you can pick up signals from advanced civilizations out there? Well, let's look at the age of the Earth. The Earth is about, give or take, 5 billion years old. And when did we start sending radio signals out? Maybe 100 years or so, maybe a little bit more than 100 years, 150 years now. So 150 years out of 5 billion, you would pick up a signal that there is maybe an advanced civilization on our planet. That gives you the idea of how difficult it is to determine how advanced a civilization is by looking at it and receiving signals from it. We hope that by looking at many, many of these planets, we would find solar systems that are in different stages of their development in the life cycle of that solar system, if you want to. And hopefully through that, we will be able to learn how solar systems evolve and change over time. But it's going to be a very long debate, I am very sure, once somebody claims that they have picked up a signal that signifies an advanced civilization. Unless we can actually go there and prove it, I'm not sure we will ever settle that debate.
Hi, my name is Kwazi. I wanted to ask if you do, or the certain materials that you don't use so that you don't transfer microorganisms from Earth to Mars.
Yes, that's a very, very good question. We have extremely strict regulations that the United States and other spacefaring nations have signed up to. If you want to send a vehicle like the Curiosity rover to Mars, you have to basically prove that you have no chances of taking organisms from the Earth there. When I say no, there's a certain probability of taking organisms there. Before we can actually launch, people have to certify that the spacecraft has been cleaned to the point where you are below a certain probability of transferring any organisms there. And of course, the reason is, the last thing you want to do is announce with great fanfare that you've discovered an organism, and it's one that you took there yourself. So, besides that, we do not want to contaminate the other planets. So that is a very, very challenging problem for us. Those streaks that I have shown you, all indications are that we will not be allowed to land near one of those streaks today, for fear that there might be organisms alive in those areas and that we would contaminate them. We do not know how to clean a large spacecraft well enough. Small spacecraft you can put in an oven and you can bake them long enough time so that you can be sure you kill everything. It's a little difficult to put a Mini Cooper inside an oven and clean it well enough. That's an excellent question.
Let's say we find somewhere signals which could stem from an intelligent life form. What would be the chances that we could ever travel there?
Well, that's of course a very interesting question. When I was still a student in Stellenbosch University, we launched 2 spacecraft called the Voyagers. I should say we, back then I was here. The Jet Propulsion Laboratory and NASA launched 2 spacecraft called the Voyagers. They are still traveling today at about 20,000 miles per hour, which is like 32,000 kilometers an hour. They've traveled all this time since 1977, and they have just left our solar system. The first one just left our solar system. At that speed, it'll take you 80,000 years to reach the nearest star to us. So I don't know, unless somebody else can figure out a way for us to move much, much more rapidly than we do today, of any way for us to travel. Kepler 186f, if we want to go visit that, 500 light years away. So that's many, many, many generations to get there. I don't know of any way that we can actually visit them.
Hello, Doc. Welkom in Dubai.
Dankie.
My question is, I think it was Christopher Walking who said something like, if you look at the Earth, and if you look at how civilizations on Earth have interacted with each other, whenever you get a more advanced civilization interacting with a less advanced one, it almost never ends up good for the less advanced civilization. So our signals that are going out into the universe for the last, let's say, 100 years or so, what are your viewpoints on this specific topic?
Well, that's of course an interesting question. You know, the history of mankind is not very kind. to those civilizations that were conquered by an advanced civilization. On the other hand, you know, we have launched with the Voyager spacecraft 2 disks. They're made of gold, gold-plated. And on them, it's like the old, kids today don't know this anymore. It's like the old vinyl records we used to have, okay, with instructions there on pictures, which I have tried to figure out and I couldn't, how to play them, by the way. And the idea is that eventually when these things get intercepted by some more advanced civilization, they will know how to play those records. On the disk is a description using pulsars and so on that shows them where the Earth is. And it has a bunch of pictures and sounds from the Earth. I don't know what will happen when somebody more advanced than us find it. I can just hope that you know, it won't be like the sci-fi movies where we just go there and destroy everything in the end.
Okay. One more question, Doc. If you look at the extraordinarily robustness of life on Earth, I think it was in Antarctica where they found life not just surviving but thriving 2 kilometers below the Arctic sheet in a lake. Now, given that life is so robust when there's lots of water present, what are our prospects for going to Europa, and how much more of a technically difficult prospect would it be to go to Europa versus going to, for example, to Mars and landing the rovers there? Are we technically there yet in terms of the engineering of it? And how much more costly would a mission like that be? And what is NASA's prospects of this?
Those are really good questions. As I mentioned, you know, we have this congressman that wants us to go land. He doesn't just want us to land, by the way. He wants us to bore a hole through the ice and put a submarine in the ocean so we can see what's going on. It's possible. The biggest challenge for the moon, like Europa, is to land on that object because it has no air. On Mars, we at least have some atmosphere that can slow us down. When we arrive at a moon like Europa, the spacecraft will travel about 6 kilometers per second. And you have to slow this thing down somehow and land gently on the surface, which has very low gravity. So if you hit that thing too hard, you'll just bounce off again. So what we want to do with those cases is you basically have to land what we call propulsively, like we did with Curiosity. You have to take rockets that can slow you down and push you slowly as you go down to the surface. That takes, of course, a lot of weight to do it. So the biggest challenge for us today is not the technology of going there and landing. It's, believe it or not, money. It's very expensive to do that. And even the United States can only afford so many expensive missions. So right now, it is simply an issue of money. And we will probably get that eventually, but I don't think with the next mission. That'll drive the cost of that mission far too high.
I just want to link up with what he said. As you previously said, the Kepler mission has discovered quite a large amount of planets, and quite a large number of them have been gas giants, which means gaseous planets are quite abundant in the universe. How likely is it that life could exist inside a completely gaseous atmosphere without a surface to exist on?
I do not know of any theory that speculates that we could find life there. However, it's quite possible that those gas giants, especially ones that are far enough away from their parent star, that they might have moons like ours, like our gas giants in our solar system. And on those moons, we might be able to find the right conditions for life. I do not know, though, of anybody that has speculated that life could exist within the atmospheres of those large giant planets.
It's just, what if there is like an alien life form out there, and if they get our signal, how would they be able to read it, or how would we be able to read it? Because they don't understand English, and if they have like a way of communicating, then how would we understand it?
And that's a very good question. Of course, some people suggest that the signals they might receive are reruns of our television series, and that might turn them off right away. They would not think of us as very intelligent, I don't think. But anyway, it's a very good question. What we were looking for in the structure of signals when people were searching for potential signals from other civilizations is a repeatable signal, not just noise, something that is not so random. That would indicate that there is some structure to the signal, and we wouldn't know exactly what they are saying, but you would know at least that signal has some structure to it, and therefore probably was generated by something other than just the background noise. I do not know how we would make contact. It looks easy in the movies, but I don't think in real life it'll be that easy for us. But on the other hand, if you put all the minds of the smartest people together, maybe we'll figure out a way to decipher it.
My question is, you sterilize all of the rovers that go to Mars as completely as you can, but there's this long-term program of sending people to Mars, and they're going to have to bring their own organisms and their own plants and animals in order to live there. So what kind of measures are going to be taken to make sure that the rest of the planet isn't contaminated?
That's an excellent question. Keep in mind that the humans will not be able to live on the surface just like we do today. You just walk outside. They will have to create a habitat in which they can survive, create oxygen and things like that. If you want to have some fun, watch the movie called The Martian that's coming out soon that speculates about how that might happen. But I would assume that we would sterilize the outside of those habitats well enough. But there's no way once you get humans there to completely safeguard the rest of the planet. And that's something that we still have to work our way through. We still don't even know how we would ensure planetary protection in that case. But that's part of the reason NASA doesn't think we can take people there until about 2033 or so.
And then I just have another question quickly. So that moon that's orbiting Saturn that is busy spewing water out through the vents, does it have an atmosphere that contains that water, or is that water just being lost?
Nope, the water is just being lost. In fact, it turns out the water eventually joins some of the rings of Saturn. It just has no atmosphere, so the particles just drift away from the moon. So if you permit me just a second, Daryl, can you bring up that other slide? Especially for the kids in the audience. I was trying to figure out a way that I can display my cell phone screen for you, but we had to go the second best option. If you're interested in playing a little bit more with some of the spacecraft that we have launched from JPL, you see up there the banner's called Spacecraft 3D. That's an app that you can download for your iPhone, your Samsung phone, your Android phone, or your tablets. It's a free app that you can download, and then you can select whatever spacecraft from NASA and JPL you want. In this particular case, I selected the rover, and then you can play around with it. I parked it outside my office, as you can see. Some kids have posted some images where they park it in the driveway of their house and things like that. It allows you to manipulate the rover. You can drive it around, all kinds of things like that. Any of our spacecraft that you can pull up like that in 3 dimensions. So if you want to play a little bit with it, just look for Spacecraft 3D. It's in the Apple App Store, and it's also in Google Play Store. You can just download it for free and play it to your heart's content.
Okay, last question of the evening.
Good idea, sir. Referring to Mars, you spoke about the variation in methane gases. You spoke about the variation in wind speeds. Is there any way you can tell me the wind speeds, the methane gas readings? At which time of the day is it at its maximum? As I'm of the opinion that the magnetic field is not cooperated. I'm of the opinion that magnetic field is solar powered. So is there any way you can tell me which time of the day are those fields at its maximum?
At least where Curiosity is, we have a weather station
Yeah.
on the rover, so we can measure the wind speed and direction and so on. The winds, it's pretty much like the Earth. The winds pick up during the warmest time of the day.
That's the key, sir. That's the key. What time is the warmest time of the day on those planets, sir?
It's, in the case of Mars, depends on what part of the season it is, but it's roughly just about 2/3.
Maybe 1 o'clock, sir?
Around 1 to 2 o'clock in the afternoon.
Thank you, sir.
The local time. That
Thank
would
you,
be
sir.
the equivalent of our 1 to 2 o'clock. Of course, their day is slightly longer than ours, but that.
Okay, I'd just like to invite the local organizing committee to say a word of thanks to the speaker of this evening.
Good evening, everybody. I must say, I don't know about you, but I'm feeling a bit dazzled. And it's not by all of you, but by a fantastic presentation we had this evening. You can think of all the great questions, that has sort of ignited science in different ways. There's probably no question more profound than whether there's in fact life beyond, our world. But I can't imagine a question that could be more fun to try and figure out. I've actually been sent up here empty-handed. Apparently there's a gift on the way. But all I can offer is that we thank our speaker one more time for truly an amazing journey that he's presented and taken us on this evening. Thank you.
Thank you very much. Thank you very much. Appreciate it.
And he hasn't, I'll say one more word, this has all been made possible by the organizing committee. And this evening I'd like to thank Patrick Vogt, for leading us through the evening. But most of all, I'd like to thank all of you for coming and making this truly a special evening that will linger, I would say, for years to come. Thanks very much.
Thank you.